Okay, tip of the week. This week you will learn about the git ignore file. The git ignore file is a file that you can add to your repository, and it will allow you to ignore certain file types in the Git version control system. So the idea is that if your project becomes bigger and you type in git status, then it will list you loads of files that are not really, that maybe just temporary files, backup files, kind of compiled files, and they will all show up in your git status as untracked files. And it will actually tell you use git add to add these files. And so you really want to avoid accidentally adding these temporary files, right, and backup files. So it would be nice to tell Git to just say, no, I'm not interested in caching files. I'm not interested in compile files. Just always ignore them. And that's exactly the purpose for this git ignore file. So the way you do this is in your repository, you just create a new file called .gitignore, and it should typically you position it in the root directory of your repository. And in there, in each line, you just specify which file type you want to ignore, or which files you want to ignore. So you can also use these wildcards here to say that you're not interested in any files that end with .pyc. And at the end, you just add that file to your repository and commit it, and that's it. So for example, in the example above here, if you look at this, this is a PyAdjoint repository here, and it has all kind of files that I don't want. So there's a .cache, there's a docs_build, and then there's these pyc files. These are partially compiled Python files that I'm also not interested in. So I created this gitignore file, and I specified start.pyc. So everything that ends with pyc I'm not interested in. Then the .cache directory I'm not interested in, which is here. Then also .swap files I'm not interested in, and so on. And after I added that, I can again type in git status, and now the output is just, okay, there's nothing to commit. The repository is clean. Yeah, that was the tip of the day. Any questions? No? Do you think it's useful to have a tip? Yeah. Okay. There's one question. Yeah. Yeah. Okay. So if you have ideas for tips of the days, then you can also send them to me. Okay. So we stopped at redirecting and combining bash commands. And I showed you the pipes just now. So we combine different programs using the pipes. But we can also redirect outputs directly to a file. And we do this by the smaller and the larger sign symbols. So in this example up here, we take the output of that command and write it directly into a file called myfile.txt. So whatever, in this case, it's just hi werden. So that's the output of the command, and that will be the content of myfile.txt. You can also append the output of a program to an existing file, and you do that by just using a double larger sign. And this also works not also for the output, but also for the input. So you can use a file as an input to a command. So normally, when you use this command wc -w, you have to, and once you execute it, the command is waiting for you to type in stuff. But if you use this minus the smaller sign here, then instead of having to type it in, whatever the content of my file will be used as a input to that WC program. So here's a quiz again. Here's a simple program. So we, I let you look at it for a second. can you think of a way of how we can simplify this program? Okay, that's one idea up there.
Can't you just type the ls output to the bracket?
Okay. Yeah. Can you explain what's going on?
So there you're taking the output from the ls command and writing the file to file of it.
Yeah, a file called files. Yeah.
And then you're executing a command to get some things from the files file that contain the word or the string.
Yeah.
Instead, you could just send the output from ls directly to the graph.
Yeah, very good. So in the first part, so the double sign just means that I'm executing two commands sequentially.
They are not the same.
Pardon?
They are not the same.
They're not exactly the same, but in this case, they end up with the same result. But
Well, in the quiz, if ls fails, grep will never start.
yeah, that's a very good point. Yeah,
And
Yeah.
if ls fills up the disk, it will probably die and grep will never start.
yeah, that's a good
If
case.
it runs forever, it will cancel. There's a bunch of differences.
Yeah, that's a good point. So there's the error handling is different in this case. So that's an important to be aware of. But just in principle, both these solutions here allowed us to communicate between processes. And so in the first case, we use files to communicate with them. In the second case, we use pipes. But yeah, as was pointed out, there are some important differences when it comes to error handling, for example. Okay, so here's the second quiz. So now, can you think of a way how we can simplify or rewrite this code? Any ideas? Yeah?
You send the content of the INF file as standard inputs to the script.
Yeah, exactly. So in the first one, I'm using the cat. So cat just writes out the content as a file to the standard output. And then I pipe it into the test script. And in the second case, I'm just using the smaller symbol to pipe in directly the content of the text file into the test script. Do you know if are there any differences in that case as well, or are these?
Well, obviously, the first case, the test command will start. And in the second case, it won't start.
Yeah, yeah.
And if we do some initialization that can break your setup, then, well, we break your setup.
Yeah. Okay. So I mentioned these standard in and standard out and standard error terms. And so it's important to be aware on what this actually means. So in general, in Unix commands, they typically have, a Unix process typically has a standard input. And so this is what, so this can be, this is a text input that is passed into the process. And then the output of the process is typically a standard output. So this is what you see on the screen. The standard error, this is you typically also see this on the screen, but it's actually a different stream, and you can differentiate between the two. And then there's an error code. And so that error code we already used sometimes. It's this question mark, the $? Variable that you can evaluate. And that error code is typically 0 if the command was successful, or non-zero if it was not successful. And so now I will show you how you can differentiate between these different parts, between these different outputs here, the standard output and the standard error, which can often be useful. And that's done by so-called redirecting the process streams. So if we execute this command up here, we will see both the standard output and the standard error just on the terminal. So if there's any errors while we're deleting these files, we will see these errors directly on the terminal. Maybe we are interested in the outputs as a file and we want to document which files have been deleted, we can do this by redirecting the standard output of that command into a file. And the standard output is indicated by this 1. So the way you should read this is that 1 stands for the standard output, and we're redirecting the standard output into the file out.txt. Okay? So if you run this program now, you will not see any standard output anymore on the terminal. Instead, it will all end up in the file. If there's an error, you will still see the error on the terminal, but it will not be in the file. It also works the other way around. So in this case down here, the errors will now be written to file, while the standard output will still be visible on the terminal. And then finally, if you want to just redirect everything to file, then use the N symbol. So this redirects both standard output and the standard error to file. Sometimes it's also useful when you write a script and you're hitting an error case, right? Then it might be useful to actually print something, and not through the standard output channel, but through the standard error channel. And the syntax for that is written out here. So you take the echo command. So the echo command writes to standard output, but then you're redirecting that standard output to the standard error. Right, so that's how this works. And then you can actually combine this again with pipes. So in this case here, I have a compile program, and the compile program might write something to standard output, but it might also write something to standard error. So I want to make sure when I pipe this into my less command so that I can pachinate through the outputs, I want to make sure that I see both. And so what I do is I take the standard error and redirect it to the standard output. And so in this case, everything that comes out of the compile command will be standard output, and I will be able to view it in the less command. So let's look at a classical Unix script, and let's see how we can work with this, how we can start writing a script around this. So here's an app that we have. It's called Pulse app, and it takes some arguments. So it takes this CMT argument, it takes a case name here, and then it also takes some inputs. So there's some configuration file that I need to write, and I need to pass that into the app using standard input. And then I also pipe the output using the T command. So the T, that's a really useful one. It allows you to redirect something to standard output, but at the same time to a file. So if you want to see something both on the standard output, but at the same time document it in a file, you can use T for that. So if you have kind of a fixed, if you know that you're only always going to run this specific command, then it's no problem to just write that up into Bash script. But there's a few problems here. So first of all, I can't really change the command line options. So if I wanted to have a different case, let's say, then I would need to open up my shell script and edit the shell script and run it again. The second problem is that this output file in which I'm documenting the output, it will be overwritten if I run the script twice. So so that's not ideal. I would like to kind of keep all the outputs of all the runs that I've performed before. And then it will also be useful to be able to, instead of me having to kind of write these configuration files, it would be really useful if I could just have some command line arguments, and then from which, instead of having to write configuration files, I would just be able to steer this program using command line arguments. Right? So the question here is, can we maybe generate the configuration file from the command line arguments that the user provides? So in other words, I want to write a script that makes it easier for me to run these simulations here. So for the first part, we would like to, the first thing that we can do is obviously we can start using parameters and start introducing parameters in our script for things that we use often. For example, we can introduce this case parameter, then we can use all the parameters that we pass in, but also we can start using the command line argument. So in this case, if the user provides a position argument, then I use that as the CMT value, and if not, then I just use the default. Then I also have kind of a default configuration file, which is hard-coded for now, but at least it's a parameter, and then also the output file. And so now when I run this command in my script, then I just use these parameters up here. So that already gave me a lot more structure in the program and a bit more flexibility in that now I can provide the CMT variable as a command line argument. So that might be good enough, but maybe we want even more flexibility. The second problem was that we keep overwriting the output file. So there's a few options what we could do. The first one is the following. We could store the output file in a directory that contains the date and including the minutes and the seconds. And at least that gives some kind of certainty that we are not overwrite the data multiple times. So the way we do that is we create a directory chopped here that is in my current directory. So this $pwd is just a variable that contains the current directory in which you're in. And then I have create a subdirectory that has as a name the output of the command date. Remember, when you use the dollar and the bracket, then you're executing the command and storing the result as a variable. So I create now a directory name that is kind of unique to my current time and date. And then I create that directory, and I go into it, and then I call the script. Right? So in that way, now when I run the script multiple times, I create new directories where I store all the results. So that's one useful approach. To make it a bit more usable, what we can do is we can always keep a link to the most recent one. And that's what I do down here. So I have this directory latest, which is just a link that points to the latest one that I've executed. So what I'm doing basically is I check if that link already exists. In that case, I delete it. And then the last line, I create the link that points to the latest job directory. So that's good. Other ideas on how we can avoid overwriting files is we could use every process in Unix as an ID, and we could use this ID in the directory name. That would be one approach, and the way you do this is with a variable that says $2. The problem is that when the process IDs are not really unique. So in particular, if you restart your system, you start reusing the same process IDs. So that's not really a safe way. Unix comes with a script called maketemp that allows you to create directories with a unique name. So maybe that would be another approach. Finally, what you could do is you could actually check if a subdirectory already exists, and because then you run into the risk that you're overwriting a file. And if that already exists, then you just exit the script and you say, well, make sure you already have some outputs there, maybe just delete them or move them before you run the script again. So this I've implemented down here. So it's this if statement down here. This checks if a directory already exists. So the -d here specifically tests for existence of a directory. So if that evaluates true, then I print out an error message down here and exit the script early. And if that directory does not exist, then I just continue with creating the directory, and then I can move on. Does that make sense? So that comes us to the if statements. So there's actually multiple ways on how we can implement if statements. I'll show you some here. So the first syntax is that you use these square brackets notation. So you say if, then a space, square bracket, space, and then the condition that you want. And then followed by a then keyword, then the commands that you want to execute, and then by an fi keyword to finish up the if statement. An alternative form of writing this is these square brackets can be replaced by the test command. Right? So instead of using the square brackets, you can just have call the test command here instead. Otherwise, the syntax is the same. And then there's a really short way of writing if statements, and that's by using these double ends. And so the way why this works is this double end does the following. So it first executes the command on the left, and if that command was successful, then it continues and executes the command on the right. Right? If that command on the left is not successful, then it just stops early. So then it won't execute the command on the right. And so essentially, the logic is exactly the same as above here, and you end up with an if statement. And so this works both with the square brackets and with the test command. So the third problem in our script now was that we had these input files that the script expected. And it becomes quite annoying if you want to maybe you want to just quickly test different setups. It's really annoying to constantly edit these input files. So it would be nice if we could just provide all the parameters as command line arguments and then generate the configuration file automatically. So the reason why this is important, because some applications, they just simply don't take command line arguments. They really need you to, they do expect an input file. And so I'll show you now how one can do that, right? So we basically want to generate the input file on the fly while we run the program. So for that, we need to learn how we can read and write files, and in particular, how we can write multi-line files. And the way you do that is you use the cat command, and then we redirect the output of the cat command into a file. So in this case, it's my file. And then the input of the cat command is specified down here. And so specifically here, we used a multi-line input. And so with this keyword up here, whatever comes afterwards will be used as an input to the cat command up to the point where it sees this end of file statement down here. So there's a keyword up here, end of file, and the input is being read up to the point where the same keyword is found down here. Right? So in other words, after running this command, you will have these 5 lines as the content of my file. So this is how you can write multi-line text into a file. So then we need to learn how we can pass command line arguments. So one option would be to basically have a while loop and loop through all the parameters that we have. And that's how we do here. So remember, the $# was the array of all command line arguments. And what we do is we loop over, we check the size. This is the size of the command line arguments. So we do have a while loop as long as the command line arguments is larger than 0. And in the while loop, what we do is we always extract the first command line argument and store it as a variable option. And then we use the shift command to eat up the first command line. So the shift command just removes the first command line argument from our list. So we kind of keep eating one command line argument after the other until none is left. And then down here we have an if statement, or in this case we've implemented as a case statement, where we check which command line was being passed in. And so the idea here is that we want to implement two command line arguments, -m and then a value, or -b and then a value. So we have this case checking here, and if the command line argument was -m, then we do exactly the same trick. In order to get the value, we write m equals $1 to get the next positional argument, and use the shift command again to eat up that argument. And we do the same thing for the b positional argument. And so the star argument here just covers all the other cases, and if there's an invalid option, then we just print an error message to the user. So after this, we can print out the command line arguments that have been passed to the user. Of course, instead of using this case, we could have just used an if statement. So this is exactly the same code now, but we used if statements where we check if the option string is -m or if the option string is -b. Works just as well. So now we know how to write to files, and now we know how to read in command line arguments. So in order to now generate our configuration file, we need to combine the two. And so that's now relatively easy. So we use the cat command. We use the file name here is just a variable called infile. And then the content, here we can also, part of this might be now hard-coded, but part of this now will be depending on the variables that the user passed in. So here in the text file, I can just do the variable substitution to replace whatever I pass in as an argument will show up here in the configuration file. So this is how we can dynamically generate these configuration files from command line arguments. Okay, and so after we've generated that configuration file, we can just run in our script, we can run the program that I want to run with this generated configuration file as an input. And then finally, maybe it's worth to add a check to make sure that the execution was successful. And so here we can use the trick with the $question mark sign. So I have an if statement where I check if the command was successful, and if not, then I print out an error message and exit early. Okay, so that was quite a so that was quite a kind of an advanced script where we were reading out and generating files on the fly using inputs and outputs and so on. So I've already showed you one way with this while loop and eating up the position arguments. So that's one way you can treat arguments that are passed into the program. There's also other approaches. You can use a for loop down here, as shown down here. So you can just write for argument in, and then remember the $@ symbol was an array of all the arguments that are being passed in. So instead of doing this eating, you could have also done a for loop. One thing that I want to mention here is when you run programs and you want to have many arguments, you can write out all the arguments explicitly. So for example, test test1.i, test2.i, test3.i, test4.i. So these are kind of .i are my configuration files, and I'm explicitly listing all the configuration files I want to have run here. What I can also do is I can use this wildcard notation, and Bash will automatically substitute this start.i with all the files that match that pattern. So if I have 4 files in my directory that stop with .i and that have the name test1, test2, and test3, and test4, these 2 commands will actually be equivalent, because Bash will, before it starts executing the run command, it will do this expansion of the file names. So that's quite a useful trick. So here's a command that here's how we can use the for loops for file management. Let's say I want to delete all the temporary files, but also have some additional, maybe some additional commands while we're doing that. So what I do is I first get all the files that are temporary files. So remember this special dash here executes a command and then stores the result as a variable. So here now we have all the temp files, and now I loop over them. And for each file, I print out a special message and then actually delete that file. So that allows you to really easily loop over configuration files, delete files, and obviously you could add more if statements in here now if you wanted to. Sometimes it's nice to have counters. Maybe you want to count the files that you've deleted as you while you go along. And so the way you do that is you create in this case we can create an integer that we set to 0. And then whenever we want to increment that counter, we use the arithmetic expression. So we can either use the let command that I've showed you before, or we use the double bracket notation that also does arithmetic expression evaluation. So this line just increments the counter by 1. And then if I print out the counter again, then now the counter will be 1. So that combined with the loop, you can now have a variable n that is 1 at the beginning, and then in your loop you can increment that n and, for example, print out the position of the command line argument, if that's what you're interested in. Yeah, sometimes you see kind of these C-style for loops. I don't think we need to go into detail, but as so often in Bash, there's multiple ways on how you can achieve the same thing. So I wanted to show you one more example. So the idea here is let's write a script that takes in a bunch of files and combines them into, bundles them into one file, but that file should be executable, and when we execute it, then it should unpack itself automatically again. Right? So it's a self-extracting, we want to write a script that generates self-extracting files. So here's a usage example. So let's say we want to call this bundle, and then it takes 3 files. And we want to store the output then into a file called onefile. But then when we call this file as a Bash script, then it should unpack itself again, and these 3 files, file 1, file 2, and file 3 should be back. So that script is really easy. What we do is we loop over all the command line arguments that have been passed in by the user. And then there's a simple echo saying we want to, we're unpacking this file now. And then we write the following. We write the content of I. Let me see. How did this work again? Sorry. No, sorry, that's right. So remember that this bundle script here, whatever we output will be written in a file called one file. So everything that the bundle file writes to the standard out should be executable bash commands. Okay? So that's why here in the first line, what we do is we call echo, but then what we actually write out, this is a valid bash command, right? So specifically, the bash command here is echo unpacking file $i, right? So this will, when we run the script later on, it will write out to the standard output unpacking file and then the file name. And so the second command that we write out to that file will be cat. Okay, so we were writing something and we're writing it to $i. So we're writing it to the file name that we want to unpack. And then what do we want to unpack? It's a multi-line file. That's why we have this end of file notation down here. Well, you can actually choose a different one, but I chose end of file here. And then I add all the content of the file $i. Does that make sense? So the point is now, so let's try this out. So let's say I have two files. File 1 contains just some text, and then file 2 just contains some numbers. And now if we run this bundle script here on these two files, okay, now the output will be the following. The output will actually be a bash script that I can execute again. And it will be echo unpacking file 1, and then a cat command that writes the content of up here into a file called file 1, all the way up to where we get an end of file. And then the same thing for the file 2. Okay, so we created a script that generates scripts for unpacking files. Isn't that cool? Yes. I'm running out of time, but I would like to show you, let's see. These are not really so important, but this is, the find command is really an important one that I just want to mention at least. So the find command allows you to traverse through directory trees and execute commands for every file that it finds. So as a very basic example, here we call the find command, and we're interested in all the files in the directory scripting./source that have the name oscillator and then something afterwards after it. And then we just print out the results. So this script just finds all the files with the specific name that start with oscillator. Now you can make this more complex. So this is basically the filtering, right? So you want to filter out specific files. You can add OR statements to that with the syntax down here. So here you have it's this special bracket syntax, but essentially, and then the -o just ends the OR statements. But essentially now we're looking for all the files that are either .ps files or have in the name end with .eps file. So yeah, so you can already see that this find command can be combined to to find quite powerful searches on your file system. But what's really useful is that you then can also execute a script for every file that it finds. And the way you do that is you add the exec command, the exec statement to it. So essentially you just have an exec argument and then the command that you want to have executed. And that for that command, this curly brackets is then a placeholder for the file name. So for example, if you wanted to delete all the PS and EPS files, you would just write -exec rm and then these two curly brackets. Then for every file that the find command finds, it will execute the rm statement, the rm command for that file name, and it will delete that file. So you can make these even more complex. So here I'm looking for files in my home directory that are of type file. So I'm not interested in directories, only files, and that have at least 1 megabyte as a file size. And then I want to execute the ls command and also print out the size of these files. So that's how I do here. So I use the type command here to filter out only files. That's what the F stands for. And then I use the size argument to filter out files that are at least 2,000 blocks. And each block has 500 bytes. And so you end up with at least 1 megabyte. So you first kind of print them, and after you've identified the files and checked that you don't need them anymore, then you can run exactly the same thing, but now I want to replace the exec with an rm minus f, and then the curly brackets. So I first list them, and then I delete them. And then finally, you can use this minus OK flag here that will tell the find command to ask you before it executes each command first. So then you have to kind of confirm that you actually want to delete them. Okay, but I think there was enough bash for today. So let's stop. And we continue. So one thing, so next week we start with Python. And I will actually give a kind of a crash course Python for 2 weeks. So in case you're already familiar with Python classes, modules, and testing, I will also talk a little bit about testing. In that case, you're more than welcome to just stay at home and maybe look through the lecture notes.